All right. So in this section, we're going to be solving systems using this method called the elimination method. And then we're going to, well, first we're going to introduce differential operators, a new notation for a differential operator that will help us in solving these things. So yeah, I mean, back in algebra, we studied systems of linear equations, and we're going to do the same thing here, but they're going to be linear differential equations, but the idea is the same. All right, so to get started, in order to solve these, we're going to be introducing a new notation for the differential operator, and it takes a little bit to get used to it. Not too much, but it's a little tricky at first. So I want to quickly review what a differential operator is. Remember this notation here? Okay, so that's an operator. It says to differentiate the thing that follows it, whatever the function is, with respect to t. So it operates on something. So for example, if we have a function y that's a function of t, we can differentiate it, and you can write it more compactly that way, right? So these two things mean the exact same thing. Also, when you want to differentiate, if you want to differentiate, do higher order derivatives, all you have to do is apply the operator iteratively or under composition. So for example, if you start with a function y of t and you differentiate it, you'll get a new function. And then you differentiate that, you get another function. Okay, so it's composition of functions. It's not multiplying. It's multiplying if you consider that, composition. But, and you could write it more compactly like so. Okay, so that notation is great. We also have the prime notation, the Newton's notation. But there's another notation that turns out to be really useful, especially for this section, and that's the big D notation. Okay, so we're going to use this big D to represent the differential operator. So for example, if we have this, this differential expression, we've got a second derivative there and a first derivative here, zeroth derivative there. We can express it using the differential operator big D like this. So this guy could be represented like so. You notice the d squared because it's a second derivative. And then this is what we're acting on. This is what we're operating on, the y. And then same thing over here. We have the 4. And then we're differentiating the y just one time there. And then, of course, we leave the 3y alone. Now, when you write it this way, one thing that you can do with the notation is you can factor out anything in common, any of the functions in common. So they all have a y function in common. So we can pull that right out to the right side, like so. And now we have basically this operator over on the left, which is kind of a combination of operators, but it's a new operator, d squared plus 4d plus 3. Okay, so we usually denote the outside operator with parentheses around it, like so. And yeah, this is telling us what to do to that function y. And the d squared right there, I'm sure you guys understand that that's a second order derivative, but remember, d squared represents, one way to think of this is it's d times d. But it's not really a times like we're used to working with times, right? We're interpreting times as being composition. So you're going to take d of y and then take d of that result. Okay, so if you want to find d squared of y, the y function, you would take d of y and then take that result and take d of it again. So what about this operator? So what if you have something like this? Well, if you have an operator like this, basically, if you wanted to act on a function y like so, you kind of work how composition works. You work from the inside out, just like we always have from algebra. It means you're going to apply this operator to y first. So you can see I put that one in parentheses. And then you're going to do that. And then whatever result you get out, you're going to apply this operator to it. Does that make sense? Okay. All right, so the first three, these are pretty basic problems. They're just a little bit of algebra in here, so let's try it out. All right, so we've got an operator, right? It's kind of a combination of operator, the big D operator, and some constants there. Okay, so we want to show that this operator is equivalent to this operator. All right, so let's show it. So to show it's equivalent, we have to show that it does the same thing to any function we give it. So let me give it some general function y, and let's apply this operator to y, and let's make sure that it's equivalent to this operator evaluated at y. Okay, so let's start on the left. So I'm going to take this operator up here, and I'm going to operate on the y function. Then I'm going to use our notation from up above that says if I have an operator times an operator, I work the inside one first. So I'll put parentheses around the inside one. All right, next, let's push the d plus 1 to the y, or another way to say it is we'll pull the y into the d and pull the y into the 1. So we've got the derivative of the y function plus the y function. Is that part okay right here? Okay. All right, well, now let's do something here. Let's actually differentiate the y function. So we're differentiating y with respect to t, which can be expressed as y prime. And then y, we can just leave that alone as a y. So now this is our new function in here, y prime plus y. We're going to apply the differential operator to this function using the same rules we had above. So I'm going to pull this into the d. I'm going to pull it into the 3, like so. Is that okay? All right. And then let's see what's next. All right. Now I want to differentiate the sum here. The differential operator is linear, so we can push it right through sums. You guys have known this since Calc 1. You just push derivatives right through. So there's dy prime and dy. That's where this comes from. Oops. And over here, we can push the 3 to both, like so. Now the derivative of y prime is just y double prime, and the derivative of y is just y prime. We've got some common terms there. We'll add the y prime and the 3y prime together to get 4y prime. And now we've got it completely expanded out in prime notation. So now what we'll do is we'll re-express this in d notation, hopefully to get back here. Okay, so this is d squared y. This is 4d of y. And this is 3y. And you'll notice all of them have a y in common. So I'll pull that y out the right side like so. And now I have that operator. And what we've shown is that this operator acting on any function y is equivalent to this operator acting on the same function y. Does that make sense? Okay, so after doing this, maybe you notice that, well, this seems like a waste of time. Can't I just multiply d plus 3 times d plus 1, kind of like a polynomial, right? And get this? Seems like a reasonable question to ask, right? Why do all this work? Okay, so that's definitely where we're going. You can't just do it and just say that it works. We need to prove it somehow. So I'm going to go through and I'm going to show the opposite direction. I'm going to switch this to the opposite side. And we're going to show it's also equal to this. And that will be enough to show that these d operators, or operators that involve d, act like polynomials, although there is one small catch. Okay, so let's switch it around here. And we're going to ask a very similar question. You notice the only difference is I switch the order. Okay, so the question is, does switching the order cause any problems? Hopefully not. If not, then it does act like a polynomial. So let's see, if we switch the order, I'll let you guys work through this on your own. Actually, why don't you guys read through that? I'll give you a minute to just think through it. It's probably better if you guys read through it. I'll give you 2 minutes here, and I'll be right back. You can let me know if you have any questions on that, okay? Right back. Okay, is there any parts in there you're confused about? It's not too bad, right? Okay. All right, so assuming you can get through this, what we've shown is that reversing the order doesn't matter. We still get d squared plus 4d plus 3. All right, so that's a real good thing. So that means that we can treat the differential operator. If we pull it out to the front, we can kind of treat it like a polynomial, which is super helpful. And that's what we're going to exploit in this section. That's going to allow us to solve systems efficiently. So there is one thing though. It's like we definitely have shown that if we reverse the order, it doesn't matter. And you might say, okay, well, does this always work? And it doesn't exactly always work. It only works when the coefficients are constants. So as long as you have a 4 or a 3, as long as there's no t in there, then you won't have any issues. Remember, t is the independent variable. So for example, you can't treat this like a polynomial. The problem is the 4t. Okay, it's actually not the 4, it's just the t, that's the issue. Okay, so I'll just show you why it doesn't work. What we're going to do is we're going to take this operator right there on some general function, and I'll show that it's not the same thing as this operator on the same function. You'll notice they're the same thing. I just reversed the order. So the question is whether or not reversing the order, do you get the same result? And you don't. So let's just take a general function and let's start with this one. So there's my function y, and here's my operator that I'm applying to it. So we'll apply from the inside out. So the first operator I'm going to apply is this one, and the derivative of y is just y prime. Okay, so this is my new function. So I'm going to push my function through or pull it to the d, pull it to the 3t like so. Differentiating y prime, that's just y double prime. And 3t y prime we can leave alone. Now it's fully expanded in prime notation. So now what we'll do is we'll write it in d notation. Let's see, this is d squared y, and this is 3t y prime. So let's see, the y prime would be the dy right there. You'll notice both terms have a y in common. So we'll pull that function out the right-hand side, and this is the equivalent operator, d squared plus 3td. Kind of makes sense, right? Just push the d through up here. Okay. All right, but what if we reverse? Well, if we reverse and we apply to the y function, let's see, we're going to apply the inside one first to y. So we'll push the y to the d, push the y to the 3t like so. And the derivative of the y function is y prime. We've got a 3ty there. Is that part okay? Okay, but now we have to differentiate this function. Okay, so we're going to push the d to each part. And the derivative of y prime is just y double prime. The problem here is, though, look, you've got two variable functions. Y is variable, right? Because that's some function of t. But then you also have this 3t in front, and that's a variable. So whenever you differentiate a variable function times a variable function, you have to use the product rule. Okay, so we'll use the product rule here. So we keep the y double prime, and you've got, depends on how you remember it. The way I remember it is first d second plus second d first. There's the derivative. Is that okay? All right. All right, so now we've got this thing fully expanded. Let's move back to d notation and pull out the operators in the front. So let's see, y double prime is d squared y. The 3y we can leave alone. And the 3ty prime would be 3t dy. And you'll notice all three terms involve a y. You've got a y there, and a y there. So we'll pull the y out to the right side. And now we've got our operator in front, which is d squared plus 3t_d. That's not what we were expecting, right? Yeah, we were hoping that this would act like a polynomial. It's not. You can't just take the d times the d and the d plus the 3t like we could over here. So because of that, just be careful. We're not going to really run into too many of these, although you'll have some questions about them. If you have a t coefficient, you can't treat these things like polynomials. It interrupts the interaction of the d operator because of the product rule. All right, so now that we got this d notation down, and we know that it works like our operators or polynomials in d, our operators act like polynomials in d, we can exploit this to solve systems. So we're going to start off with second order systems. So here's a coupled system. So it's in two variables, x and y. Have I mentioned that word coupled before? Okay, so a coupled equation is just, or a coupled system in x and y is when at least one of the equations has both x's and y's involved. Because what that means is if they're both involved, then if you change one, it changes the other. Or if you change x, it changes y, or change y, it changes x. So whenever you have that happen, the system is coupled. This system is definitely coupled. I mean, depending on what the constants are, but it's got x's and y's in that equation, and that's enough to be coupled. And so is this one. Okay. Now, this is a second order equation system. So the way you can tell the order of a system is you look at the order of the equations and you add them together. So if we look at this first equation, the highest order is 1. So that's a first order differential equation there. And if we look at the second equation, that's also a first order equation. So that's 1. So we just take 1 plus 1 to get 2. So this is a second order system. Is that okay? Okay, so there's our system. And then this guy over here is some function of t, right? Could be 0, could be anything, right? And then the coefficients in front, the a1 through the a8, those are all constants. So there's no t's involved there. They're all constants. So here's our goal. Our goal is to find the solution to the system. That means we're trying to find two functions, x of t and y of t, that satisfy the system. When we plug these into the system, both equations have to hold. Okay, so what we're going to do is exploit the new d operator, the big D notation. So let's take our system and let's rewrite it using the big D notation. So I see some primes there. So this x prime can get replaced with dx. This y prime can get replaced with a dy. And this x prime with that dx, and this y prime with that dy. That part okay so far? There's a lot of notation in here. Okay, so next what? Oh, I forgot to mention one thing. You know, it's important that you have your system in standard form. So that means basically you want all your x's over here on the left kind of clustered together, and you want all your y terms on the right, and then whatever's left over, put on the other side. That part's really important because they don't all come that way. So make sure they're in standard form. All right, so now that we've got this thing expressed in big D notation, let's apply it to the x's over here. You notice both of these contain an x, so we'll pull it right out the side. So we've got a1d plus a2. Is that okay? All right, and both of these contain an x, so I'll pull it right out the side. So I've got a5d plus a6. We'll do the same thing over here. Both of these contain a y, so we'll pull that y out the side. A3d plus a4, and then we'll also pull that y out. Is that okay? All right, so listen, this is the big idea. this is kind of looking like a linear system from algebra. So what you want to notice is you've got basically X is over here. And you've got Y's over here. And then some other functions over there. What we'd like to do is use kind of the same technique we did in linear algebra, or I'm sorry, in algebra, where to solve a system, basically what we want to do is eliminate a variable. So what you want to do is pick one of the variables to eliminate. There's only two. There's just an X and a Y. So, you know, and then you guys know how to do the elimination method. You take the top equation, multiply by something, the bottom equation, multiply by something, so that these are negatives of each other, so that when you add the equations together, you eliminate the X. But when you eliminate the X, what you're really saying is you're uncoupling. You're getting an equation that's uncoupled from X. Once it's uncoupled from X, then you can solve that equation for Y. And now you have Y. So then what you want to do is find another equation that's uncoupled from Y, which is an equation in X, and then you can solve that equation for X. Now, solving is going to involve differential equations. So, that's going to be the heavy work. But the big idea here is the same as algebra. All right, so let's just take a look at an example, and then we'll go through the formal procedure. All right, so first of all, what's the order of this system?
Second order.
It's second order because it's got two first order equations in it, right? And what are the variables we're trying to find?
X and Y.
Yeah, you're always trying to find dependent variables in differential equations, X and Y. And the independent variable here is T. And when I say solve for the dependent variables, X and Y, those are functions, right? So we're solving for those functions. All right. Oh, here's something else I forgot to mention. If you have a second order system, it works just like differential equations. I'm sorry, like equations. For a second order system, we can expect two constants in our solution. If it's a third order system, we can expect three constants. Okay, remember the constants of integration, the C1, the C2, C3, so on and so forth. This one should only have two. Okay, so whatever we get out for a solution, in fact, I'll show it to you. This is the solution that we're going to get. Do you notice there's only two constants in there? There's a C1 and a C2. That's it. Okay, so that's one thing you want to go look at right from the get-go. What else? Okay, is this in standard form? No, it's actually in normal form. If you remember normal form, that's where you have the highest order derivative solved for. So we need to first rearrange this thing so it's in standard form. So kind of move everything around. For the first equation, move everything around, get the X's on the left, and then the Y's, and then anything left over on the right. Do the same thing for the next equation, like so. So now we've got all our X's here, Y's, and then your numbers. And then we're going to convert to D operator or big D notation. So this X prime gets replaced with a DX. This Y prime gets replaced with a DY. And then this part's important, right? These both have an X in common, so we'll factor that X out. And then these both have a Y in common, so we'll factor that Y out. And now this thing is set up. And hopefully now you can start to see the idea of what we're going to do. We're going to use elimination to kill one of the variables. So you get to kind of choose, but in this case, let's go ahead and eliminate X. So if you want to eliminate X's here, the coefficients have to be opposites. And right now they're definitely not opposite. So what I notice is that this coefficient is missing a -4, and this one is missing a D-3. So I'll take the entire first equation, and I'll multiply the whole equation by 4, because it's missing a 4. And then I'll take the second equation, and I'll multiply the whole thing by D-3. Now, the whole point of this is that now these are opposites of each other. That one had a negative, so it stayed there. Now that they're opposites of each other, we can add the equations together to get an equivalent equation or get a true equation. Okay, so let's add the equations together. These guys are gone now. We constructed it that way. And if we add these equations together, look, we've got 16y here. Got this guy here. And 4 plus this guy on the right. Okay, so these are all y terms. So if you want to, you can jump right down to this step, the second step. Because basically you have 16 of the y's, right? And then you have d plus 7, d minus 3 of the y's. So that's the total number of y's you have. And over on the right, we have 4 plus 10d minus 3, 10d minus 3 of t. Push the t through. And then the derivative of t with respect to t is 1. So replace that with a 1. Let's just finish the right-hand side. Might as well, right? Is that okay? The right-hand side's usually not bad. Look good for the right? Okay. Now on the left, now that I've got the y kind of factored out to the right, it makes it really easy to simplify the operator. So you could just work with these operators, you know, these are like polynomials in D. So just work with them like polynomials. Just, you know, FOIL this thing out, rewrite it like so, make it look a little nicer. And then what you can actually do is you can factor that into this composition of operators. D plus 5, D minus 1. All right. Okay. So what we have now is an uncoupled equation in y. We eliminated x. So we've got an uncoupled equation in y, and we should be able to solve this equation. This is a second order differential equation with constant coefficients. It's non-homogeneous. Okay. If you wanted to write it out, here it is. Y double prime plus 4y prime plus 5y equals 14 minus 30t. You might be able to see that here. There's your d squared of y. There's your 4d of y. And there's your minus 5y. Is that okay? All right, so how do we solve these things? Well, this takes us back to a couple areas. You know, to solve any one of these differential equations, we have to find the homogeneous solution and the particular solution, because we definitely have a non-homogeneity. And then we're just going to add them together. So we got to find YH and YP. So to find YH, you set this equal to 0. And to find YH, we'll set this equal to 0. And we'll write down the corresponding auxiliary equation, go through, find those roots, exponentiate them, add them together. And then we'd also want to find YP as well. And what method should we use? Oh, I wrote it down. You're going to use undetermined coefficients to find YP. Okay, so assuming you can do that, and we'll do one in just a few minutes, the general solution, this is what you get for the homogeneous, that's what you get for the particular. The general solution for y is given right there, where C1 and C2 are the arbitrary constants in the homogeneous part. Okay, so are we done? Did we solve the system? No. Yeah, we got halfway there, right? So that was a lot of work. By the way, this part in here is going to take some time, right? Just to find the just one solution of the two. You have to use both of those methods. So that's going to take some time. Okay, yeah, we still have to find the other one. So what we want to do now is basically find an uncoupled equation in X that we can solve. And there's two options for doing this. The first one works 100% of the time, but it takes longer. And the second option is a shortcut, but it doesn't always work. So we're going to go through the long way first, and then hopefully you'll appreciate the shortcut after that. It does work in this particular, for this particular problem. So let's do the long way first. All right, so I'm not going to show all the steps, but what you could do is you could go back to the original system here, expressed in big D notation. And instead of eliminating X, we could eliminate Y. Just redo what we just did. Okay. Now, assuming you did all that work, you would arrive at this solution right there. Of course, you'd have to use the auxiliary method and undetermined coefficients, which is a pain. It's a lot of work to do that, right? The problem is you're still not done, because if you write both of these down, there's your solution to the system. There's a problem. What's the problem here? Why is this not the solution? It's close. We just have to do one more thing. Anyone see it? How many constants do you see?
4,
You got 4, but how many should we have?
2.
We should only have 2. So what that means is a couple of these constants are dependent on the other 2 constants. So in other words, we should be able to express, let's say, K1 in terms of C1 and C2, and express K2 in terms of C1 and C2. That way we've reduced it down to just 2 constants, which is what you need if it's an initial value problem, right? Okay, so yeah, we have some more work ahead of us. So yeah, and also be careful. Don't write a C1 and C2 there, because you've already used up the C1 and C2 when we found our solution for Y. So they truly are different constants. Okay, so so we've got our solution pair. We've got too many constants. So we need to find the dependencies. I need to figure out how 2 of them depend on the other 2. So the idea is simple. If you want to figure out how they relate to each other so you can solve for 2 of them, all you have to do is go back to one of your original equations. This is the first equation. This is at the very, very top, right here. And then what we'll do is we'll just plug in our solution for X and Y. And then we know it has to be true. What'll happen is I'll have K's and C's in there, and I should be able to expand out, equate coefficients, and solve for K1 and K2 in terms of C1 and C2. And that's what we're going to do. So here's my first equation in the original system. I've already found X and I've already found Y. So let's go ahead and plug those in. So there's the X in there. Of course, you have to differentiate it. There's the prime. I'll plug my X in there, and I'll plug my Y in there. We've got lots of practice with equating coefficients. So we'll take this derivative on the left. We'll move everything around. Let's move all the exponentials to the left and collect them all. And I've just got numbers on the right, which simplify to 0. E to the negative 5t and e to the t, those are linearly independent, so they don't combine into each other. So what that means is the coefficient in front of e to the t over here must be 0. And that's because that's the coefficient on the right, right? Oops. So I have to equate that 0 with this guy. And then same thing with the negative 5t. So this is going to yield this system in let's say K1 and K2. Let's say those are the 2 variables we're interested in solving. So let's solve for K1 and K2. You guys can do that. You end up getting K1 equals C1 over 2 and K2 equal 2C2. Okay, so we've determined the dependencies. So that means whenever I see a K1, like we did above, we can replace it with the C1 over C2. And whenever you see a K2, like we did here, we can replace it with a 2C2. And now we have what's called the general solution. So you got to get rid of the dependencies, the extra constants, when you write out your general solution. Okay, is that okay? Okay, so that's the long way. The reason why it's long is because of that dependency stuff, right? You got to plug it in, equate coefficients, and it's a pain. But there is a shorter way, but it doesn't work all the time. So here's the shorter way. So we've already solved for Y, right? So y is a known variable. The unknown variable is x. So if we can somehow come up with an equation that involves the unknown variable x, the thing we're trying to find, and only known stuff, well, we know y. We can find y prime, so that's known too. We should be able to just plug in y here and then solve for x. Does that make sense? We've already got y up here. So the question is, where did this come from? Well, this came from the second equation. This guy right here. She'll notice that the equation involves an x, which is what we're trying to find, the unknown x. And it involves a y, which is known, and a y prime, which is known. So we should be able to solve for x. But here's the problem. Let's say that there's an x prime there. We couldn't use the equation if there was an x prime. So why is that? Remember, x is unknown, right?
Because we have what x prime equals right above it, right?
Yeah, x is unknown. So if you didn't know x, you're not going to know x prime either, right? Okay, so then you'd have two unknowns, and yeah, sure, these are known, but how are you going to solve for x there? You're not going to be able to solve it because this thing is an unknown. So it's only going to work in certain situations, right? So however, I mean, so look for an equation here, see if it works. Look for one here, see if that works. Or if you want to take a multiple of one and to add it to the other, maybe you could come up with one where there's no x prime involved. In this case, it was easy. It's just that one. But in your homework, you might come up with one. It'll require you to do a little thinking there to use the shortcut. But it's worth it. It'll save you some time. So anyways, here's the equation we're going to use. This is equivalent to that the second equation in the first system. So all you have to do is plug in your y. So we'll plug in our y there. Remember, this is our y, our known solution. Plug in our y there, just to do some simple algebra, and then we've got x. Do you guys notice you don't have to, there's no K1 or K2 or anything like that here, right? So this is much faster. But again, it relies on the fact that you can find an equation for the unknown variable completely in terms of the known variable y. Okay, so that part's important. Okay, so we've got our general solution. So there's the y, there's the x. And so there's our general solution. Notice we have two constants, which is what we expected. Is that okay? Okay. All right, so finally, we're going to generalize what we just did. And we're going to create something called the elimination method. This is going to solve systems. Let's see if I can find one. Here we go. This is a second order system, two first orders. The elimination method will handle this fine, but it'll also handle higher order systems of equations in two variables. So if this was like a third, fourth, fifth order differential equation, you could still solve it using the elimination method. So let me show you the theory, and then it's pretty quick, and then we'll jump into the method. So we still have two unknown variables, x and y, so that hasn't changed. And the one that we were working on before, those were first order linear equations in the system, but they don't have to be first order. So what we can do is, let's say we have this system. And you notice I'm using an L sub I. So what do those represent? Well, think of each of these L's as representing a polynomial in D. For example, it might be d to the fifth plus d squared minus 2. Okay, that's d to the fifth. We haven't worked with that. That's a fifth order derivative, right? So that would be a derivative of order 5 in there. So imagine that L1, L2, L3, and L4, they're just polynomials in D, and I don't care about the order. They don't have to be first order. So we can use the elimination method to solve the system no matter what the order is. using the same technique we used in that example above. Basically, just write down your system. You want to, let's say, eliminate the y's by multiplying the top equation through by L4 and the bottom equation by L2, negative L2. That'll yield this system. Is that okay? And the purpose of this is that these guys right here, if I add them together, the y's will cancel out and I'll get an uncoupled equation in X. Okay. Now, what we can do now, okay, so here's the uncoupled equation in X. So once you add them together, L4, L1 minus L2, L3, X. And then we have L4, F of 1, I'm sorry, L4, F1 minus L2, F2. So this would be your uncoupled equation in X. And then what you could do is you could just go back using, you know, basically what we did in option 1 and just eliminate the other variable this time by multiplying the top equation by L3, the bottom equation by negative L2. I didn't write it out, but what'll happen is you'll get an uncoupled equation in Y. And each of these equations we can solve. Now, here's the thing. We've only really worked with first and second order equations as far as solving them. But you guys have solved a couple of third orders in class. The theory is pretty much the same with the auxiliary equation stuff, and same with the undetermined coefficients, the particular solution. It's the same idea. So you're going to have maybe one or two in here where you'll have like a third order, but the idea is completely the same. All right. Okay, but this is where that issue arises. When you do this multiplication, it kind of doubles the order, or it multiplies the order when you multiply these two guys together. And because of that, what ends up happening is when you solve the system, each of them is going to have n constants. So when you add them together, you're going to have twice as many constants as you should have. Okay, so then what you do is you'd have to reduce down to n constants using the technique above. But once you reduce it down to n constants, then you'd have your general solution. That okay? Okay. And then also one other case, do you guys remember this from solving linear systems? Remember this from algebra? If you've got two lines, usually they like cross, right? So when they cross, there's a solution, and you guys know how to find that solution. Now, the ones that we usually do are kind of analogous to like the crossing type. There's going to be a solution. But you remember lines can also do this, right? So what happens when lines do this? What do we say about the solutions? This is back in algebra. You would say there is no solution, right? There's no solution. Okay. All right. And then there's another case where the lines lie right on top of each other, in which case you would say what?
All solutions.
There's infinite solutions. Okay, so the same thing can happen here. And it's analogous. If you go through the math, it's almost set up identically to it. And that's going to happen when you add the equations together and one of these guys zeroes out. Usually that's not going to happen, but when you have one of those cases, one of those will zero out, and then you'll get the identity. You'll get the zero operator, which is basically the identity. It doesn't change anything. And if you have that, you kind of have the analogous situation to either being parallel or on top. So what could happen is you could have, the system is said to degenerate in that case. And what can happen is you could have no solutions, or you could have an infinite number. Okay, so I don't think you have any questions about that, but just in case. All right, so now let's formally state it. I'd like you guys to just read through this on your own just for a second. It's basically a summary of what we just talked about. This is probably what you're going to be referring to. Ask me if you have any questions in here about any of this in blue. Let me know. So I'll give you a minute to look through that. That okay? Okay. Just basically a summary of what we just talked about, okay? But this is probably where you're going to go to like, as far as the steps go. All right, two more. All right, so we're going to solve this guy. So first of all, do you guys recognize that as a third order system? Okay, it's because this one is a second order equation and that's a first order equation. So we just add them together to get order 3. So right off the bat, we know something about the solutions. We know the general solution is going to have 3 constants, a C1, C2, and C3 usually. Okay, what else do we know? It's pretty much in, oh, I got the X over there. It's almost in standard form. We'll have to move that over, but okay. All right, so let's try this out. Let's first move it into standard form. So I've got all my X's here, then Y's, everything else left over on the right. Then we'll express this using D operator notation. So I'm going to skip right to that. Is that okay? Once you get comfortable, you can start skipping around a little bit. Okay, and this one is just D plus 1 of Y. And that one's D of Y. That one's D minus 1 of X. Is that okay? All right. So next, the idea is the same. We're going to eliminate a variable. By the way, these guys in front, these are the L1s and the L2 and the L3 and the L4 that we discussed prior. Okay. You don't need to remember the L. It's insignificant. It's just showing you the theory, right? The D is the thing you want to remember. Okay, so let's eliminate Y. So let's see. This guy has a D plus 1Y, and this one's just a DY. So what we can do is this guy's missing a D, and this guy's missing, let's say, a negative D plus 1. And then if we add them together, the Y's will cancel to uncouple, to get an uncoupled equation in X. So let's do that. Let's multiply the first equation through by D and the second equation through by negative D plus 1. Now, when we add these two, they'll cancel. Okay, so here's all our X's here and our X's there. Okay. So I kind of like going right to this step. But you don't have to. If you just want to write down the addition there, that's fine. But this is how many X's you have, and that's how many X's you have here. So just that's how many X's you have, right? So I'm going to have D squared minus 1D. So there's your X's, number of X's up there, and here's your number of X's. So just add them together. So I usually just go to that second step. The Y's are canceled, and over on the right, D of negative 1. Let's just do the right hand side here. We can do this quickly. D of negative 1, that's 0. We can push the T squared through to each part. Make sure you incorporate that negative there. Derivative of T squared is 2T. So there's your right hand side. The right hand side, okay? Okay. And then on the left, what we're going to do is, since we have the operator completely isolated out front, we can play around with it, try and factor it, simplify it down. So, so you could expand all this out if you want, but you don't have to, because look, D plus 1 times D minus 1 is D squared minus 1. So I've got a D squared minus 1 there, and I've got another D squared minus 1 there. I can factor the D squared minus 1 out of both of these terms, which leaves me with a D here. And it leaves me with a 1 there, or a negative 1 there. That okay? Okay, so there's our uncoupled equation in X. This is a differential equation. I know it's weird looking at it like this, but what's the order of this differential equation? Yeah, and how can you tell? So Sebastian said order 3. How can you tell it's order 3?
You have a D squared and then the D.
Yeah, because if you were to multiply this out, right? So the highest D squared and D, that's going to be a D cubed. So it's a third order. Okay. Now you might notice that right off the bat, we kind of have a little bit of an issue, because when I solve this, that's going to involve 3 constants, right? It's third order. So the general solution for x is going to involve three constants. But how many constants should I have for the entire system? I should have three, right? And I'm using up all of them on the x. So I think what's going to happen is, we might have some extra ones if we don't do that shortcut. So we'll see what happens here. Where are we? So there it is. Okay. All right. So yeah, to solve this thing, we're going to use the auxiliary method to solve the homogeneous case when that's 0. And then we're going to use the undetermined coefficients because that's just a polynomial that's suitable, right? So we can use undetermined coefficients to find YP. So we should be able to find YH and YP. And there they are, just kind of foreshadowing there. All right, now I do want to show you like a little time saver that you might not notice. You probably would if you did the problems enough, but here's what happens. When you find YH, look what happens here. So the first thing you might want to do is you might want to expand this to get d cubed minus 2d squared minus d plus 1, and then write it how you're used to, right, with prime notation. And now that it's in prime notation, then you would write down the auxiliary equation, and then you'd factor the auxiliary equation, right? But here's the thing. Why waste your time? It's the same thing, right? You're just replacing the D's with R's. Does that make sense? It's the auxiliary equation is baked inside right there. When you have it factored like this, that's why we factor everything, kind of prep us for using the auxiliary equation. All right, and this thing's relative, that's pretty easy to solve. That's just, we've got a double root of 1, and then we have a negative 1. So we did one of these where we had 3 roots back in section 4.2, I think. But yeah, so the solution is going to look like this. And you're going to notice, let's see, so that'd be e to the t, and e to the negative t. Where did that extra t come from right there?
Double the same root.
Yeah, it's because when you have a double root, you remember this from section 4.2 case 2. This is when you have a double root. You're going to add in an extra factor of t. That way these guys are linearly independent. And their solutions too. Okay, so there's YH. So I'm sorry, XH. We still have to find XP. Oh, that's a misprint right there. I should read X. Okay. We still have to find YP. I'm not going to go through this. You guys can do this on your own. But what you want to do is just look at the non-homogeneity up here. And it's a polynomial, so it's suitable. It's second degree. So the form of your solution should look like that. That's a general poly second degree. That okay? All right, so then you're going to solve this thing. It's a bunch of work, but you guys can do it. And you're going to get these for the constants. So your particular solution is found just by replacing those constants. So there's XP. So now that you have XH and you have XP, you can finally write down the solution for X. So there it is. And you'll notice we've already used the 3 constants. Is that okay? All right, so that was a big pain. So I'm really hoping the shortcut works on finding the solution for Y, right? That would just be mean if it didn't. Luckily, it does work here, okay? So so solving for Y, the shortcut works. So let's go back up and see. Let's see, we know X is a known solution. We're after Y. So we want to make sure that we have an equation that involves our unknown Y and then only known things. It can't have a Y prime in it, only Y's. So what you'd want to do is go back up here to 24 or one of the original ones. I went to this one here, but it doesn't really matter. This one isn't going to work because it doesn't even involve y. And this one isn't going to work either. But what we can do is subtract the equations. If I subtract the top one minus the bottom one, or the bottom one minus the top one, the y primes will cancel, and I'll be left with a y. And it'll be completely in terms of the known variable x. So that's what we do here. I did it in the big D notation just for practice. So if you guys want to do that, it's fine. Subtracting, and then there's that equation solved for y. You'll notice there's my unknown and then my known variable x, and it looks like I only need the second and first derivative of x, but we can find that because we have x. Are you guys following okay? This stuff's kind of dense and it's just hard to know, but I hope you guys got it okay. Can you give me a thumbs up if this is kind of making sense? Sort of? Okay. All right. Okay. All right. All right. So if you can get the idea with this and then go back and look through it more carefully, that's a good idea. I know that the big D notation is weird, but after a while you'll get comfortable with it. Okay. So look, we've got X, and then we've got a relationship between Y and our unknown, and then the thing we're trying to, our unknown, and then the known function X. So all we have to do is plug in our known. So if you plug in your known X value there, looks like we're going to take a second and a first derivative. So there's your first, there's your second. This is basic algebra. You guys could simplify that. Looks like you're going to have a product rule in there, maybe twice, but it's a very easy product rule. Simplify the thing out, and now we've got our solution for y. So there it is. There's your general solution. And yeah, there's your three constants that we got initially with x, and it turns out we don't have any more. We use the same ones. Notice this one only uses two of the constants, and that's okay. Is that okay? Okay. All right, so we got one more. Now, this last one is a system of equations in three variables. Turns out we can use the same method. The problem with this one, once you get into this deep, it's hard to keep track of everything. So when you guys are writing out your work, try and be very neat. Maybe partition certain parts of your page to designate to certain ideas, because it's just a lot. If you just write straight down, you're not going to know where to go to. So, so here it goes. So, what's the order of this system? It's third order, right? So it's got three first orders in it. The system's written in normal form, which we don't want. We want to rewrite it in standard form. So let's take the system first of all, and let's write it in standard form. So we can write it this way: all the x's over here, then the y's and the z's. By the way, it's third order, so we're expecting three constants, right? C1, C2, C3. Okay, so then you're going to rewrite using the D operator notation. Is that okay? You guys okay with that? Looking for nodding heads. Looks good. Okay. All right. All right. Then we want to factor the x out, or factor all the variables out. So x, y, and z, like so. And then what we're going to do is we're going to label the equations. I would suggest doing this because it's just a lot to keep track of. Okay, no problem, Paulina. Now we're going to solve this the same way we solve systems of three equations in algebra. So can anyone give me a synopsis or like a summary of how do you solve an equation in algebra if you've got three variables involved? What's the big idea?
You cancel out one variable to get, or you cancel out one variable twice, and then you get one system of two equations, and then you solve there.
Yeah, so if you've got three equations, right? You pick two of them and you eliminate a variable. Let's say z. Okay, so now you have an equation, an x and y are just kind of sitting over here. And then you pick another two and you eliminate the same variable. Okay, so now you've got two equations over here in x and y. So then you put this on the side and you bring in your smaller system, right? So your smaller systems in x and y, and then you could solve this one like we did above. Once you solve this one for x and y, well, you've got 2/3 of the problem. All you got to do is take those two solutions, plug them into any one of the original equations, and then you can solve for z. Okay, so the trick is reducing this down to a 2x2 system. All right, so equation 1, 2, and 3. Okay, so I'm going to go through this quickly. I think it's probably more helpful for you guys to read through the details in your own. So we'll just go through the big picture stuff. So we're going to create a smaller 2x2 system by eliminating one of the variables. The variable I'm going to eliminate is going to be z. So what I'll do is I'll pick equations 1 and 2, these guys. And the reason I'm eliminating z is it's so easy to eliminate it right there. I'm just going to add them together. So if we add the equations together, I'll get this equation, which simplifies to this one, which simplifies to this one, which simplifies to this one. That's what you get if you add equations 1 and 2 together. You'll notice what this is it's a differential equation in two variables, x and y. All right, so let's hold on to this. We're going to need it to create our smaller system, right? And then I'm gonna go back and I'm gonna try and pick another pair and eliminate the same variable z. So what we'll do is we'll multiply equation 2 by d minus 5. What am I doing that for? Oh, I'm getting in preparation to add it to equation 3. Okay, so I multiplied the second equation through by d minus 5 in preparation to add it to equation 3. And when you do add it to equation 3, you get another equation with no more x's or no more z's, which simplifies to this guy, which is another equation in x and y. So now we've got these two equations in x and y that we know are both true. So we'll take these and we'll create this smaller system. Now this system only involves x and y, and we should be able to solve for x and y using the method above. And then once we're done solving for x and y, then we could take our solutions and plug them in for z. Okay, so to solve the smaller system, you do it like we did above. I'll let you guys work through the details here. You'll arrive at this uncoupled equation in y if you eliminate x. You can solve that using the auxiliary method in undetermined coefficients. This one doesn't have any repeated roots. And then solve for the other variable x here. You know, you might have to do it the long way, but hopefully not. But it turns out that if you add the equations together, you do get an equation that you can use to solve where x is the unknown and y is the known. Since you already know y, you can plug it in. By the way, this shortcut doesn't always work, right? You might have to use option 1, which sucks, but read through this. We went through this. I don't want to go through it again. It's kind of get the big idea. Maybe put the word shortcut up here or something. Okay, so then when you take your known solution y, you plug it in, push the operator through, simplify, and there's your solution for x. So now we've got x solved for, and we've got y solved for. You notice we're using the same constant since we used the shortcut. But okay. And by the way, the system was third order, so we've already used up the constant. So that would have added some extra work for us. All right. And finally, and this is the easy part, just take your two solutions, your x and y, and plug them into any of the original equations. It doesn't matter which one. Where is it? Any of them, because you're going to know x and y. When you plug them in, you'll be able to solve for z. Or I should say any of them that involve a z. All right. If it's a z prime, then, then you'd have to integrate. So try and find one that involves a z. All right. So there's z. Oops. We're going to take the second equation. We'll plug in our y and our x, take the derivative of the y there, and we've solved for Z. So finally, when we write them all together, this solution triple is called the general solution to the system. That okay? All right, guys, that was pretty much it. Thanks for coming today. Let me turn off the recorder.